Hello, welcome to this clip going through the Chemistry Olympiad, Round 1, 2006 paper. This is the first question, and it's about sherbet lemons, so obviously a nice start to the paper. And it starts off by talking about the main ingredient in sherbets that give them their classic sort of fizzy sensation on the tongue. So we're looking at 2,3-dihydroxybutane-dioic acid. So part A, it says that assuming all the sugar present is sucrose, which is C12H22O11, write an equation for the complete combustion of the sugar. So some tips to consider would be that all carbon atoms become CO2, as opposed to carbon monoxide or remaining as carbon. All hydrogens become H2O, so the O atoms already present, so 11 of them, need to be included when you're deciding the balancing number for the oxygen from the air. So the first part is balancing for carbon and for hydrogen, so you have 12 carbon dioxides and 11 waters. So we have a total of 35 oxygen atoms on the right hand side. And we have 11 oxygen atoms in C11H22O11. So that means there's 24 oxygen atoms that are needed from the air. So in other words, you need 12 oxygen molecules to react with one molecule of sugar. So it's a 1 to 12 mole ratio. Okay, so the next part is the standard enthalpy of combustion. So when it says minus 5644 kilojoules per mole to the minus 1, that means that 1 mole of sucrose releases that amount of energy when completely burnt according to the equation we've just worked out. So they want us to calculate the energy released when one sweet containing 6.70 grams of sucrose is completely burnt. So we need to get 6.70 divided by the molar mass of sucrose. So that gives us 0.01959 moles, which in turn is 111 kilojoules, rounded to 3 significant figures. Okay, so the next part, this is about working out how many sweets an adult male needs to consume in order to meet his needs. So his dietary calories per day is about 2,500, so to meet that requirement, he'd need to consume quite a few actually, as it would look like. So 24.426 is one sweet, so we need to divide 2,500 by that number. So working on 111 kilojoules per sweet, this leads us to 103 sweets. It's actually slightly less, about 102.3, but you know, who's counting? So if you look at the mark scheme, it actually has 95 sweets. That's because they use the 110. So you can have 110 kilojoules or 111 kilojoules. Each one will lead to a slightly different number of sweets. You would get credited for just doing the right processing, and you wouldn't actually get penalized if it was slightly up or down. So provided your number of sweets matched the number of kilojoules that you worked out in one sweet, then you'd be fine. So let's now go on to part D. So at this point we're looking at gas volumes. So it explains why the fizzing sensation happens. We mentioned it slightly earlier. So the fizzing sensation occurs when the tartaric acid reacts with the sodium hydrogen carbonate. So I've put the ionic equation there to help explain and illustrate what they mean. So in a lab experiment, one sherbet lemon sweet produced 6 centimeters cubed of carbon dioxide. So the thing to do now is to draw the structure of 2,3-dihydroxybutane-dioic acid. So there's our structure, and the hydrogens that would go into the equation, the ionic equation provided at the top of the screen, are in red. So 1 mole of tartaric acid would react with 2 moles of NaHCO3.